Hi there, my name is Mr. Chick and I'm here to tell you about electricity generation. This video has been designed to help students understand how generators, motors and transformers work. The first thing to look at is induction. When a magnet is moved through a coil of wire, an electric current is induced. This happens because as the magnetic field lines are cut by the wire, a potential difference is set up through the wire. This causes the electrons to flow. This phenomenon is called electromagnetic induction. Note that an electric current is only induced if the magnetic field lines are cut. If the magnet does not move, then no potential difference is set up in the wire, and so no current will flow. It is for this reason that the current induced is an alternating current. We can increase the amount of electricity generated in three ways. First, we can increase the strength of the magnet. Secondly, we can increase the number of coils of wire. Thirdly, we can move the magnet faster. I should also mention that we can also use a soft iron core to increase the amount of electricity induced. Finally, if identical magnets are used, whereby their poles are opposite, we can see that no current will be induced. This moves us on to generators. Another way to induce electricity is to spin a magnet within a wire coil. Again, you can increase the electricity induced in the same way, as well as using an iron core within the coil of wire. This method is far more practical. This principle is used from small handheld dynamo devices such as wind-up torches to large-scale generators in power stations. When you spin a wire coil inside a magnet, you produce alternating current. This is because every half turn of the coil, the current is induced in the opposite direction. This is a result of the potential difference flipping position on the coil. As one side of the coil comes up through the magnet, it induces current in one direction as it cuts the magnetic field lines. When it comes down through the other side, it induces a current in the opposite direction. This is a result of the direction of the magnetic field lines relative to the motion of the coil. You can work out the direction of the current, the motion of the wire coil, and the direction of the magnetic field line using the right-hand rule. The magnetic field lines are always north to south. You can observe the direction of the motion, either up or down, so you can work out the direction of the current. I will show you this hand rule later on. Slip rings attach the coil circuit to an external circuit. The slip rings are connected to the external circuit by brushes. The brushes allow the electric current to flow from the internal to the external circuit. The two slip rings attach to two separate ends of the external circuit. This type of generator is an AC generator. A split ring commutator replaces the two slip rings in order to convert the alternating current into direct current. The commutator has two sides that are insulated from each other. When the coil turns, the split rings turns with it. As a result, the direction of the current is always direct because the induced current always flows to the same contact brush on the external circuit. Okay, so now we can look at motors. When a wire carries an electric current, it has its own magnetic field. This is the concept of an electromagnet. Electromagnets can have their magnetic properties switched on and off. When a current flows, the wire becomes an electromagnet. When switched off, the wire no longer acts as a magnet. When the wire acts as an electromagnet, its magnetic field interacts with the magnetic field of the permanent magnet. Consequently, a force is exerted between the wire coil and the magnet. You can use Fleming's left-hand rule to work out the current direction. The north side of the permanent magnet is attracted to the south side of the electromagnet, whilst the north side is repelled. The problem with this is that the coil of wire needs to spin continuously in order to do mechanical work. The electromagnet will become fixed if the circuit is always complete, and therefore it would not rotate. We will look at Fleming's left-hand rule at the end. This is the role of the split ring commutator. The wire coil's momentum carries it through the point where there is no contact. When the wire coil makes contact with the external circuit, the wire coil becomes an electromagnet once more and interacts with the permanent magnet so that it repels it. This cycle continues over and over to produce mechanical work. This is the motor effect. So we can look at how generators and motors compare. The generator and the motor only differ in that the generator uses mechanical work to induce electricity, whilst the motor uses electricity to produce mechanical work. They are in effect the opposite of each other. Okay, so our final thing we'll look at transformers. Transformers have a simple role. They're used to either step up or step down the voltage. They work on the principle of electromagnetic induction. A transformer contains two sets of wire coils connected by a soft iron core which runs through them both. The primary coil contains an electric current and is wrapped around one side of the iron core. The secondary coil does not have an electric current and is wrapped around the other side of the iron core. An electric current can be induced in the secondary coil. In order for the secondary coil to induce an electric current, it requires a changing magnetic field. The only way that this is possible is by having an alternating current in the primary coil. By doing this, a changing magnetic field is run through the soft iron core. Consequently, the changing magnetic field passes through the secondary coil and induces an electric current. The way that the voltage can be stepped up or down depends on the number of coils on the primary and secondary coil. A step-up transformer has more coils on the secondary coil. A step-down transformer has less coils on the secondary coil. So here our example is of a step-down transformer, as there are less coils on the secondary coil. This is because the ratio of the voltage of the primary over the voltage of the secondary is equal to the ratio of the number of coils on the primary over the number of coils on the secondary, and this formula is showed here. So we'll look back at our two hand rules. Our left hand rule is for the motor effect, and our right hand rule is for generators. My name has been Mr. Chick. I hope this video has helped you. Thank you for watching.